So let's think about the domain of combined functions. When we add or subtract or multiply the combined functions, then we just combine their individual domains, meaning you could just look at the domain of f, look at the domain of g, and combine them together. The special case is when we divide two functions. We're going to have that intersection of the two domains, but also we need to make sure that that function g of x does not equal 0, since it's going into the denominator. So let's see how this works. So if we have these functions f, g, and h, what can help is just thinking about their domains to start with. Well, f is linear, g is quadratic, h is quadratic, so all of those have domains of all real numbers, or from negative infinity to positive infinity. So they don't have any limitations to them. So what that means is if I start combining them, any combination that doesn't involve division, I can already write the domain down in terms of being from negative infinity to positive infinity. So addition, subtraction, multiplication, those are going to be all real numbers. But when I have division, I need to be careful of that denominator. Combining the functions, let's practice that. So find the new function and simplify. So adding the two functions together. So I would take f of x, so 3x plus 1, and then I'm going to add that with g of x, which is 1 minus 2x squared. So then adding those together, I'm just going to rearrange this like a quadratic. We're going to have a negative 2x squared plus 3x, and then we have a 1 plus 1, which would be a plus 2. So what you can see is we end up with something that's quadratic there, so that makes sense that the domain is all real numbers. If we subtract two functions, so taking 3x plus 1 minus x squared plus x, and simplifying that down, so we're going to have 3x plus 1 minus x squared minus x. So that would be a negative x squared. 3x minus x would leave us with 2x, and then we have a positive 1. So again, something quadratic is coming out, so it makes sense that we have all real numbers. Let's skip over division for a second and just look at the multiplication piece. So g of x is 1 minus 2x squared. And multiplying that with x squared plus x. And what we're going to do here is FOIL. So I'm going to have 1 times x squared, 1 times x, negative 2x squared times x squared for negative 2x to the 4th, negative 2x squared times x for negative 2x cubed. So what we have here is a polynomial with degree 4. If you take a look at the graph of that, polynomials also have a domain of all real numbers, so you'd be all set there. Okay, the division of two functions. So taking f of x, which is 3x plus 1, and then over h of x, which is x squared plus x. So with this, my domain starts as all real numbers in terms of what's good for the numerator, what's good for the denominator, except now I have this extra condition that the denominator, x squared plus x, cannot equal 0. So if I solve that, factor out an x plus 1, that cannot equal 0. So solving this is going to tell me that x cannot equal 0, x plus 1 cannot equal 0, so x cannot be negative 1. So we end up with these two limitations. So we can have all real numbers and x cannot be equal to negative 1 or 0. So with the division of h and g, so h of x, x squared plus x, g of x, 1 minus 2x squared. So in terms of combining them, we'd have all real numbers, but now we're going to say 1 minus 2x squared cannot equal 0. And then solving that, so 1 cannot equal 2x squared, divide by 2, so 1/2 cannot be x squared. And then we're going to take the square root of both sides, which will tell us that x cannot be equal to plus or minus the square root of 1/2. So with this, we'll have a limitation 2 that will have all real numbers and x cannot be equal to plus or minus the square root of 1/2. Again, with these domains, once you find this combined function, you could plug it into a graphing calculator and check the graph and make sure that, like with these rational functions, what we're seeing are vertical asymptotes come through. Okay, let's look at another example with our rational functions. So what we'll have and what can help is first thinking about how our domain's limited. So for m of x, what we'll need to understand is that x cannot be equal to positive 5, since we can't have a 5 minus 5 there. For p of x cannot be equal to negative 3. So those will be the domains that we start with. We can have all real numbers, but we shouldn't have those coming through. So finding a formula for p of x minus m of x. So p of x minus 2 over x plus 3 minus 3 over x minus 5. And we'll just leave it in that form there. And what we can see is overall the domain combines because we have the limitation from that denominator and that denominator. So we have two spots where the denominator could turn into 0. So for the domain, I'd say all real numbers and x cannot equal negative 3 or positive 5. Multiplying the functions together, so we would have 3 over x minus 5 times x minus 2 over x plus 3. So in the numerator, we'd have this multiplication. I'll go ahead and distribute the 3 through, so 3x minus 6 over, and then I'll leave these separated as x minus 5 times x plus 3. We could multiply it out by foiling, but in this form, what we can really see is how we still can't plug in positive 5, we still can't plug in negative 3, because if we have 0 in either of those spots, then we'll have 0 in the denominator, and then it would all fall apart. So for the domain, it stays the same in terms of x cannot be negative 3 or positive 5. For the division of two functions, so we'll have, I'll write this in the horizontal format, so 3 over x minus 5 divided by x plus 2 over x plus 3. So what we'll have is, we'll still have our original domain. But what we need to do is simplify this, because what we have is a complex fraction where we're dividing. So I'm going to do the keep, change, flip. So we're going to go ahead with keep 3 over x minus 5, change to multiplication, and then x plus 3 over x plus 2. So simplifying this, we're going to end up with, I'll go ahead and distribute the numerator, so 3x plus 9 over x minus 5 times x plus 2. And what we notice here is here I'm now getting a new restriction for the denominator, that x cannot equal negative 2. So I still have my original x cannot equal positive 5 there, so that's still in there. We have this new x cannot equal negative 2, and with those two, that's correct, that's part of the domain, we can't have those values, but there's this hidden value that we need to keep as part of our domain, and that's that original negative 3. And what you want to think about is that it's coming in through the combination of the two functions that has to follow through. It's also much more clear in this first step here that we should not be plugging in negative 3. It just kind of hides as we simplify it, but it's still there. So that's where when you start making these domains, you need to first think about the combination of the two functions, combine their two domains, and then at the end, reevaluate and see if there are any new restrictions to the domain. So the domain is all real numbers, and x cannot equal negative 3, negative 2, or positive 5.